Okay, so hello and welcome again. So, what we did in the last discussion was we talked about the concept of bulk mean temperature, and also we were uh, discussing about a variable phi, and that is equal to T minus TB, right? So, variable phi equal to T minus TB, where TB is the bulk mean temperature. And we also talked about that if we talk about phi b, okay, if we talk about phi b, then it was phi, right? Yes, it was phi. So if we talk about phi b, then phi b is coming as what? TB minus TB, and that is equal to 0, and that means that d phi b dz, that is equal to 0. That means phi b is not a function of z. And I also explained, okay, and I explained it very rigorously, so I will not explain it further because I already took a lot of time in explaining it. So 5 is not a function of z, then we can have, I am not saying we must have, I saying we can have phi as a function of r only, or if I define eta as my r by capital R, then eta only. I can have this, and I also told that let us try to find a solution. So if a phi, if a solution, that is phi equal to only function of r, exists satisfying the differential equation, so this differential equation I derived last time, satisfying this differential equation and also the boundary conditions, if there is a phi that is satisfying this, then we can say that yes, I can have the solution. Because what do you call a solution? Okay, a solution should satisfy the differential equation as well as the boundary conditions, right? So now let us see that if we can have that. Now before that, my question is that why we are doing this, right? That is why we are doing this, why we are doing this, right? I mean, I have the energy equation, so then I have the unknown variable as t, so then why I am declaring a new variable phi here? Okay, because I have shown you that I cannot solve this equation by the general separation of variable method. Okay, so this was the governing equation and the boundary condition for the given problem, and this was not solvable by the method of separation of variables, right? Okay, so then what I want to do is I want to modify the problem description. Okay, the ultimately it will be the same problem, but mathematically I will manipulate it so that I can have a solution. Okay, so now I mean my physics, I mean my physics that will be required to I mean to simulate the or to formulate the problem, that is more or less has ended here. Okay, but after that, to solve this equation I need mathematical manipulation. Okay, so that is what I am doing now. So let me write the governing equation again. Okay, so that will be beneficial to you. So uz, I will write this uz as w. Okay, so w into del t del z equal to the radial conduction, right? So the actual problem, so let me write the description for the, okay, no, this is too much thing. So actual problem, and that is w into del t del z is equal to alpha into 1 by r del del r into r of del t del r, right? I think I have written it correctly. Let me check once. Yes, 1 by r del del r, r into, okay. So this was the governing equation, and the boundary condition was So this was the governing equation, boundary condition at r equal to 0, my regularity condition or the symmetry condition is this, at r equal to r, my del t del r has a fixed value q naught by k, right? Okay. So I, that is my heat flux is entering, if it is entering, okay, so then minus q means it is leaving, right? So that is why it is plus here, that is minus k del t del r, that is leaving the surface, but my q is entering, so minus, if I put minus here then I have to put a minus here also. I have talked about this convention in my previous discussion in details, okay. So also at z equal to z naught, or if I consider that as 0, I have some variation of temperature, okay, maybe that is T in, and that will be a function of r because I have fixed the z. So this was my actual problem, and I told that I am not having the required boundary condition and the governing differential equation, so that I can solve it by separation of variable method. So now can I break this problem? Break this problem like how? Uh, I mean, what do I mean by breaking the problem? So I can define a variable phi, that is t minus tb, okay, and I can also break this phi, so let me write it as capital phi, okay. So capital phi is not written like this, it is like, so capital phi is this, and I will break this phi further as small phi plus psi, okay. Why I am doing this I will tell you, okay. So then ultimately you see that my t minus tb is equal to this, so then my t becomes tb plus phi plus psi. So now you might have been thinking that what the hell, why are you uh, making the uh, making the problem more complex, right? So now just have this idea in your mind that this is not the physics, but I am just making some mathematical manipulations. Obviously the answers of the solutions, I mean the mathematics will always bring some uh, new physical concepts, okay, I mean some new physical ideas that will be emerged from the mathematical manipulation, but I am doing this exercise just to solve this uh, uh, system of equations, okay. So now I am breaking these three. So this was earlier my only unknown variable. Now I have three unknown variables. So I have shown you that this is the bulk mean temperature. So bulk mean temperature is already integrated over r, then it is only a function of z, okay. But this t is a function of r as well as z, right? Then this 2 all over should be the functions of r and z, right? Now I am seeking a solution of phi that is only a function of r, okay. Then psi can be a function of anything, psi can be a function of r only, z only, or r and z. So I am taking it as a function of r and z, okay. So ultimately it becomes what, my, okay, so let me write it in this color. So my t becomes, sorry, my t of r comma z becomes tv of z plus phi of r plus psi of r comma z, okay. So I have broken down my unknown variable t into three unknown variables, okay. So now, okay, now out of this, how, so I have told you earlier that if I have to break the problem, I have to break it in such a way so that the governing equation, so let me write it actually. So governing equation of problem 1, problem 2, problem 3, okay, so if that is added, so if that is added, so then this should be give my governing equation of problem, actual problem. Okay, so this will give my the governing equation of actual problem, right? Now also boundary condition of problem 1, problem 2, problem 3, if you add them also, then it will give the boundary condition of actual problem. If this happens, then only uh, you can declare that I am applying the separation, I am applying the superposition method. And why this should happen? Because the problem is linear, right? So let us try it. Now for my problem 1, so I will do it for my problem 1, and for my problem 1 my unknown variable is TB. Okay, okay, for my problem 1 my unknown variable is TB. So I am having T equal to this thing. So how can I get a governing equation of TB? So TB is what? TB is a bulk temperature, that I can assume that if I have a control volume here and I am applying some heat here, that is heat flux Q naught, okay, and let us say that I am having some temperature T here, and this will be T plus dt, okay, because it will heat, and this is nothing but my dx, right? So therefore if I apply energy balance, what will I get? So energy entering is Q naught into area. Area is 2 pi r into dx, and that is equal to the increase in enthalpy, and that is equal to m dot Cp T plus dt minus T, right? But there is a catch, that is here the energy that is entering, now I am only considering the fluid flow, but fluid is a material and it can have conduction, so it can have axial conduction also, right? It can have axial conduction and it can have this term, right? If this is the x direction and this is y, r, okay, r maybe r, so okay, so I am taking this as z, so let me take this as z, okay, and this is also z, dz actually, okay, so this is also dz. So but I have told you that we are considering a large re flow. Large re flow means it is a large pe flow, okay, large spectral number flow, so my axial conduction is neglected. So in if I am writing this equation, I have to keep the fact in mind that my axial conduction is neglected, right? So then my, and this I should write TB, okay, that is the bulk mean temperature. I mean bulk mean temperature is what? That at any cross section, my temperature is having some variation, but it is somewhat an indicator of the average temperature. I mean for each cross section I will have one bulk mean temperature, okay. So you see here that uh, del Tv, sorry, dTv dz, that becomes what? Q naught into 2 pi r by m dot Cp, right? And my, now my m dot is what? So this Q naught 2 pi r, m dot is rho into A, that is pi r square, into W average, right, into Cp. So pi cancels out, r and 1r will cancel out, so this will become 2 into q naught rho r W average Cp. Okay, so I have got an equation for dTb dz, and here you see that my boundary condition is constant heat flux. So as my heat flux is constant with z, so that is why my dTb dz is also a constant. Okay, so therefore my governing equation for dTb dz will be this. So this will be 2q naught by rho r W average Cp. Okay, so now if I integrate this, then I will have 2q naught z rho r W average Cp, right, plus some constant. And how can I find the constant? So I have the boundary condition at z equal to 0, my Tb will be equal to the Tb initial, right. So then my C will be what? Here my C will be Tb int, right. So then I am having my Tb, solution of Tb. Okay, and you see that this is physically meaningful. So because if I am having a graph like Tb and Z, then it is showing that it was having some finite value and then it is increasing linearly, right. And because you are constantly giving it some heat, so that is why it is increasing linearly. Okay, so now I have defined a variable phi. So phi equal to uh, t minus Tb, right, and this will be my problem 2, description of problem 2. So this was the problem 1, and now I am talking about the problem 2. So I told that I am seeking for some solution that is phi equal to phi of eta only, where eta is equal to r by r, and then I got the equation, the governing equation. Let me copy it. Okay, let me copy it like this. So I can copy it and I can okay, so sorry, it sometime misbehaves. Okay, and for that I really apologize to you. Ari, I'm very sorry. Okay, so it is typing there. It is again typing there, right? Okay, so let me write it down other than pasting it. Okay, let me here do it. Okay, so let me write it down. I'm sorry for the time waste. So it was what? Actually, that is my problem. I cannot remember things very much. So 2 into W dTb dz. Okay. So 2 into W average 1 minus eta square, that is the velocity profile for the Hagen-Poiseuille flow. This is equal to alpha by maybe r square, now 1 by eta, and dd eta. Okay, dd eta of what? Eta into d phi d eta, right. I think I have written correctly. Yes. Okay, so now it is correct. Then I am having some expression for this dTb dz, and that is what? That is 2q naught by rho r w average. Okay, so that is 2q naught by rho r w average Cp, right? Yes. So finally my equation becomes 2w average. Okay, so this and this will cancel out. Okay, so let me write it here in a good way, because I am prone to making mistakes, silly mistakes. Okay, so this will be cancelled out, and then 1 r will be cancelled out, right? So then I will be having 1 minus eta square into 2q naught by rho Cp, right? Or what I can do is I can take this 2 out from here, and so this will be what, alpha by 2r, right? Is it correct? Okay, it is correct. Alpha by 2r 1 by eta d d eta eta d phi d eta. Okay. Okay. So now my alpha is k by rho Cp. So this becomes this into q naught equal to, okay, so this is alpha by 2r into rho Cp, and alpha is k by rho Cp. So alpha into rho Cp is k, right? So this will be k by 2r, this thing. How much, how many brackets I have given? Okay, so now it is okay, right? So let us see that what it has become. So if I refine it more, then it is 1 minus eta square 2r q naught by k, okay, that is equal to 1 by eta dd eta of d phi d eta. Okay, so can you tell me that is this equation is non-dimensionalized or not? So the answer is it is not, because phi is t minus tb, and eta is not having any dimensions. So right hand side is having a dimension of temperature. So also the LHS should also have the dimension of temperature, and you can write the units of q, r and k, and it will have a dimension of temperature, q into 2r by k. Okay. Now what will be the boundary conditions here? So the boundary conditions will be, so boundary conditions, right, 1 at eta equal to 0, that is at r equal to 0, my what I was having, dt dr, or del t del r actually, because t is a function of both r and c. So del t del r is equal to 0, right? And that means my t equal to phi plus tb. So tb is not a function of r, then it becomes, and phi is, we are assuming that phi is a function of r, then that is 0. So, and this will be, I can easily transform into eta, then I will have a multiplication factor of capital R, and because the RHS is 0, then I can write it as 0. So another thing is that eta equal to 1, that is at r equal to r, my del t del r was q by k, right? So that will be what? Mm, Again I will have my d phi d eta into 1 by r. I have done this transformations from one coordinate to another for several times. So this will be d phi d eta is equal to q naught r by k. Okay. Now you will say that I will have another boundary condition, that is at z equal to some 0. Okay, at z equal to 0 I am having my t equal to t init, but see that my phi is only a function of r, so it does not depend on z. Okay, so this boundary condition is not valid here. It is, so this the solution of phi is valid for any z. Okay, so that I have assumed. Okay, or rather you can write a third boundary condition like this: at z equal to any z. Okay, at z equal to, or you can write at any z phi of r equal to phi of r. Okay, that is, it is valid for any z. Okay, I mean there is no meaning in writing in this third boundary condition. And so I have now the problem description for phi. Okay, and now I think you can easily solve this, because it is an it is only having a unknown variable phi here, and it is an ODE. You can clearly integrate it and find the phi. So I will do that, don't worry. But now let me give you the problem description. Okay, for 3, and that is the unknown variable is psi. So psi is a function of both uh, r and z. Okay, so my psi is what? T minus tb minus small phi, right? So this is my psi, right? Okay, so now you see that the, okay, so I have the governing equation as t here. Okay, so now see a very interesting thing. What you do is you put this t equal to tb plus phi plus psi into this governing equation. So then let us see that what we will get. So w into del z of tb, but tb is only a function of z, then you will get here. So w into phi is only a function of r, then this will be 0. There will be no z derivative. I am writing the LHS, and this will be again w into del psi del z, and that is equal to what? Alpha into 1 by r del r. So tb is not a function of r, so that term will not contain any tb, the RHS. Now phi is the function of r, so let me write the psi here first. Okay, plus alpha into 1 by r ddr r into d phi dr. Okay, so now you see this is my governing equation in terms of tb, phi and psi, right? So now you see the I am uh, okay, so this is my minimum size of screen. So you see that this is my governing equation for tb, that is dtb dz, right? So what I can do is I can split it like, so can I split this equation like this? So I can have my one equation, so let me use deep color. So this is very interesting actually. Okay, so just keep your concentration here. So can I split it like this? Okay, that is, this is uh, okay, so I can split my LHS into this and this, okay, this plus this. So these are the two terms of my LHS. Now of RHS of psi, I will have the RHS of psi here, okay. So this is the governing equation for psi, and this is actually alike the governing equation of T, right? And now for phi, I am not having any LHS, okay, I am not having any LHS, and also for TB I am not having any RHS. So let me write down like this, okay. So now you tell me that if I add this equation 1, 2 and 3, I am sorry. Now you tell me that if I add equation 1, 2 and 3, can I get this equation, maybe equation A? I am getting it, right? So now you also tell me that if I put anything like any constant, let us say m here and also here, then also if I add 1, 2 and 3, then I have m in LHS and I have m in RHS, then both of these m's can be cancelled out, right? Then also I am getting this equation A back, right? So my so one of my conditions are satisfied, that is the governing equations for problem 1, 2 and 3 should be added, and that should give the actual governing equation, okay. And what is this m here? So this m here is this constant 2q naught by rho r w average into Cp, right? So if I write here this thing, okay, that is 2q naught by rho r W average Cp, and here also I have to write again this thing 2q naught rho r W average Cp. Then also you see that if I add 1, 2, 3, I will get A. Now you see that this is the governing equation of my problem 1 that I have already told you, right? Yes, this was the equation, and this is the governing equation for my problem 2, right? Sorry, okay. So so this is W into this, right? W into this. So this was the governing equation of the phi. So I must have, okay, so here I have a W here, okay. See that this is the beauty, that if you do any mistake, then either mathematics or physics that will tell you that yes, that you have done some mistake. So I was carelessly telling that yes, this was my problem description of 1, but see that in this equation I have a W here. So to have the actual problem description of 1, I have a W here also, then this W and this W will be cancelled out, right? So then I have to have a W here to have the actual problem 1, and if I am having a W here, I have to have the same factor here also, then I must have the W here, okay. So then you see if I have the W here, and this W is nothing but the Poiseuille profile 2 into W average into 1 minus eta square. So then you see that you are getting the exact differential equation uh, of the problem 2, right? That is the governing equation for phi, okay. So this is the problem 1, okay, and this is the problem 2. Then this must be my equation of problem 3. So you see that I was searching for a phi that will not depend for z. So what was the basis for that? So this thing you must keep in mind, otherwise you have to mug up this, that yes, he took the phi here, so that is why I mean, so that is why I am looking for phi. But my point is that the thinking process is very important here, okay. So that is why I am sharing all these things. No one has shared all these things. Okay, I have I have attended various classes, describe the separation of variable and also the method of superposition, but but actually rarely anyone explains these things, that yes, actually this is why we are getting a governing equation for psi. So then what you will mug up is that yes, I have to first solve for phi, then I have to solve for something called psi, and actually nobody knows that where from that psi has come. Okay, but the psi has come from a pure mathematical concept, that is I am having a variable tb. I have defined a variable phi equal to t minus tb, phi, that is capital Phi, and that is equal to phi plus psi, and now I know that t equal to tb plus phi plus psi. So the moment I got my differential equation for phi and tb, then I have to construct the governing differential equation for psi in such a manner so that the governing differential equations of the three problems should be added to give me the actual uh, governing differential equation. Okay, so okay, now you see that that is how I am getting the governing differential equation for psi. Another thing, you see that in thermally fully developed, in hydrodynamically fully developed flow, the main thing that if you ask any mechanical engineer that what do you know about a that is hydrodynamically fully developed flow, then he or she will tell you that this is nothing but dz is equal to 0, that is the velocity profile is not changing with z. So can we define anything similar for a thermally fully developed flow? So for a thermally fully developed flow this cannot happen. Okay, don't ever say this thing, that is del T del Z is equal to 0. This means that in the pipe you are giving heat but the temperature is not increasing, and that is not possible. Okay, so can we find instead of T any variable that is having this kind of property, that is not changing with Z, and that is nothing but phi. Okay, so I will tell you that other than phi also I can have more options. Okay, so that is why we got a variable phi which is not changing with z, and that is why we are searching for a solution that is only phi equal to phi of r and not z. So so that we can define some variable that will characterize the uh, fully developed flow. So fully developed, I mean the thermally fully developed flow. Okay, so you see that these three equations, so all these things I have told you to find the governing differential equation of psi here. So psi is having the governing differential equation alike the temperature one, right? So W into del phi del z is equal to alpha 1 by r del r r into del phi del r, right? So here now my bound, okay, so now let us see that the second condition, that is the if I add the boundary conditions of the three problem, that should give me the boundary condition of the actual problem, right? So what will be the boundary condition here? Okay, so let us see. So boundary conditions of my problem 1. Okay, problem 1 boundary condition at z equal to 0, my TB equal to TB initial, and for so TB is not a function of R. Okay, so that is valid for all R. Okay, it is valid for all R. So at R equal to R, that is for all R. Okay, so at all R okay, valid. That is TB equal to TB. Now problem 2. So at r equal to 0, okay, at r equal to 0 my del t del r is equal to 0. At r equal to r my del t, actually that was given in terms of eta, but I can write in terms of r also, because eta and r are, I mean, like the same. Okay, just there is a scaled factor of capital R. So this is equal to q naught by k. And problem 3, that is my psi. So I have the boundary condition. Okay, so now my actual boundary conditions are what? So my actual, okay, actual problem. So at r equal to 0, del t del r is equal to 0. At r equal to r, my del t del r is equal to this, and at z equal to 0, I have t equal to t in it. Okay, so here the variable was tb. For problem 2 the variable was phi, so I should write it here phi, not t. So this is phi, and here it is psi, right? So now let me see the first boundary condition. Okay, so at r equal to 0, okay, so at r equal to 0, okay, so now in the point of view of my actual problem, I have my t equal to tb plus small phi plus psi. So at r equal to 0, if I replace this tb plus small phi plus psi here, then I will get at r equal to 0, so del t del r, so tb is not a function of r, so 0 plus, so d phi dr, because phi is the only function of r, and this is equal to 0. So at r equal to r, again this will yield the same LHS, right? This is equal to q naught by k, right? At z equal to 0, so here tb plus phi plus psi, that should be equal to t in it. Okay, okay. So now that means I have r equal to 0 here, r equal to 0 here for this problem. Okay, so this is for not actually the problem 3, this is okay. So what I can do is uh, I can, sorry, I can take this part and move it to here. Okay, yes, because this is under the actual problem. Okay, so now you see that, okay, so at r equal to 0 I have to add up this 0, this thing and this thing, and RHS should be 0. Okay, so for z at r equal to 0, okay, there is nothing, and for phi, so these are d phi dr, d phi dr. Okay, okay, so if I write here at r equal to 0, my d phi dr, d psi, sorry, del psi del r, okay, my del psi del r is equal to 0. So now let me add up the boundary condition for r equal to 0 for problem 1, 2 and 3. So you add up problem 1, 2 and 3. So problem 1, there is no r dependence. So if I write this thing at r equal to 0 for problem 1, at r equal to 0, my del tb del r, so tb is anyway not a function of r, then I can write it at a 0. And also if I write at r equal to r, again I can write del tb del r is equal to 0, because tb is not a function of r simply. So you add this thing, you add this thing, and you add this thing. then you will get this thing, right? Okay. Now let us see for r equal to capital R. So at r equal to capital R, you will add this thing, you will add this thing, then what remains? So let us see that we don't know that at r equal to capital R what should be the del psi del r, we don't know that, but we know that at r equal to capital R, so del tb del r plus del phi del r, actually that is d phi dr plus del psi del r, that must be 0, and this is anyway 0, right? This is anyway 0, and this is what we have got, q naught by k, q naught by k. So then this must be minus q naught by k, and that is how you get the second boundary condition for psi. Okay, so for psi it is equal to minus q naught by k, it must be, otherwise the boundary condition cannot be 0. Okay, okay, I have done a mistake. What sort of mistakes are these? So here it is q naught by k, okay, and here and because all total you have to have the RHS q naught by k. So then this must be 0 because we already have the q naught by k. I apologize for this. Okay. So this is 0. You understand why? That is because here the total RHS from here I have to have q naught by k. So I am having del TB del R already 0 because TB is not a function of R, and d phi dr I am having the boundary condition as q naught by k. So here already I have the q naught by k and the RHS I am having q naught by k, then this must be equal to 0. So now let us look for the Z. So at Z equal to 0, okay, what should be there? TB plus phi plus psi should be T in it, right? And I already having that at Z equal to 0 my TB is equal to T in it, right? Yes, from here. And now if I have, okay, so for phi I don't have any Z dependence. Okay, so if I am having that at phi equal to 0, at Z equal to 0, okay, I don't care that what is my phi, okay, that is because my phi will valid for all the solutions, I mean for all the Z, my phi is only a function of R here, okay. So here it will be the only the solution of phi. Let me write it as phi of R. So this is the solution actually, solution of problem 2. Okay, because you take Z equal to 0, you take Z equal to any other thing, it will be the same value, the same function of R. Okay, so that means my psi should be, okay, my psi should be at Z equal to 0, at Z equal to 0, T init minus TB init. Okay, so if your T init is a, okay, so let me tell it differently. Okay, this T init minus TB init minus phi of R. Okay, so now generally we take the uniform temperature condition in a pipe inlet. So that means your T init is a constant. And if your T init is a constant, so then your TB init, that is the bulk mean temperature at the inlet, that is this, and you put that in your expression T init W dA by integral of W dA. So this T init being a constant will come out of the integral, so it will be integral W dA by integral W dA, and that will be cancelled out, that will be equal to T init. So you see, for a uniform temperature profile, that will be the TB init equal to T init. So this boils down to 0, this boils down to 0 for uniform inlet temperature. Okay, so now we have successfully broken down the actual problem into three different problems. Okay, so and now let me tell you that you have covered all almost the whole conduction. The so we are studying the convection, right? But in conduction you can have different problems. I mean, I will just change the boundary conditions, or I will add some heat flux. Then we will have uh, some different differential equation. But the differential equation that you have to solve, that will be either by simple separation of variable method, or most probably at the most complex problem you will have to break the problem into three or even more problems, so that you can apply some simpler method in each of them to solve each of the problems, and then you have to add the solutions to get the actual solution. So here we have successfully broken down the three parts. Okay, so already this video I think has got a very heavy content for you. So in this video what we have done is we have successfully broken down the actual problem into three parts. Now in the next video we will solve for each of these, and already I have done the solution for the first one, and that is very easy. That is the solution for TB, right? So what will so now the task for you will be to solve for this one. Okay, I will give you a hint. Now you see that to integrate this equation, that should not be a hectic task for you. This is so because this is a constant, and this is just a polynomial function of eta, so you can multiply this eta here and integrate, then divide by this eta here and then again integrate, and you do that. Okay, but you will see that if you apply one of the boundary conditions, so see that this is a second order ODE, so you will need two boundary conditions. I mean, you will get here two constants C1 and C2, but but if you apply any one of these two boundary conditions, you will see that automatically without solving for C2, you will get an equation that will satisfy both the boundary conditions, and that will be having the question that how can I solve for C2 then. So you have another condition, that is phi of b equal to 0. Apply that here. So you will got this phi equal to something, some expression, and that will be a function of this eta, this 2r q naught by k, and also C2, another integration constant, and your objective is to find this C2. So you find this phi b. How can you find phi b? So phi b equal to integral of phi w 2 pi r dx, okay, 2 pi r dz, okay, that is dA. Is dA 2 pi r dz? No, 2 pi r dr, right? 2 pi r dr. We are integrating with respect to r by w into 2 pi r dr, that is the dA. So apply this, and this is equal to 0, and you will get C2. I will solve this, but I insist you to solve this by your own and get to a solution of phi. Okay, so in the next discussion we will complete the uniform heat flux case. Okay, and we will get the solution, actual solution, the temperature profile, the heat flux, the Nusselt number. Okay, and until then, goodbye, take care, and thank you. If you have any doubt, post in the comments. If you have any suggestion, post in the comments.